Welcome to Relational Database Design, Lesson 4. And in Lesson 4, we're going to talk about the functional dependency, which I also italicized as FD. Our lesson is laid out in this way. We have the functional dependency theorem, where we're going to look at the formal definitions. We look at the full functional dependency, partial dependency, and transitive dependency. We have an example of finding functional dependency in a given relation. Let's begin with looking at the theorem. Functional dependency is a fundamental concept in relational database design, and we use it to find keys for relation. We also use it to check if a relation is in a good form, and good form in a sense that we ensure that data is not duplicated. Of course, we look at data integrity through enforcing some constraints, and it helps us to eliminate any data anomalies that may arise from insertion, deletion, and also update operations. The functional dependency provides a set of rules of representing relationship between attributes. And we have a definition here for a given relation R. The values of one set of attributes, which we also call the dependent, are uniquely determined by the values of another set of attributes, which we also are going to call determinant. Let's look at those two terms, the dependent and determinant. The determinant is a set of attributes on the left side of the dependency arrow. And the dependency arrow is indicated this way. In many times, this is the determining factor that uniquely determines values of the dependent. Let's look at an example of a determinant. And we say that it appears on the left-hand side of the functional dependency arrow. And this is the arrow we're talking about. The left is right over here. So any sets of attributes, for this case, we have only one attribute, A. So A is pointing towards B, and we can literally say that A functionally determines B. So that's how we write it out. And what happens to the, how do we call it? We call it the determinant, okay, which can also be more than one attribute. Okay. Dependent. Sets of attributes that appear on the right-hand side of the functional dependency arrow. We already know the arrow. Let's look at the right-hand side this time around. And we know that dependents are determined by values of the determinant. So when you look at the right-hand side, we are clearly label them as dependents. Still using the same functional dependency of, for this case, let's say A pointing towards B, but we literally say it out that B is functionally dependent on A. So the right-hand side, of course, it only consists of one attribute, which is B, and we say it's a dependent, and the dependent can also be a set of attributes, which can be more than one attribute. We have one thing to note here, that the relationship from the determinant to the dependent should be a 1-to-1 mapping. One note that we need to make very carefully here, we notice that the relationship between the determinant and the dependent must be a 2-1 mapping, and always the arrow needs to be pointing to the right-hand side. Let's look at a formal definition of a functional dependency. And let R be a relational schema. And R can be any set of attributes. In this case, we have two attributes. We have alpha and we have beta. So alpha is basically a subset of the relation R, or a set of attributes in R. The functional dependency written as alpha pointing towards B, which we now call that alpha functionally determines B, can only hold if and only if a legal relation, has two tuples that agree in values. And for example, if we have two tuples T1 and T2 on the attributes, agreeing on the attribute alpha, okay, that means they should also agree on the attribute beta. And we're going to look at an example where our relation has two attributes, A and B. So A in this case is our alpha and B here is a beta. When you look at this illustration, we have three tuples, T1, T2, and T3. So A is agreeing, okay? A is in agreement with the first tuple and the second tuple. Or you can even say it that tuple 1 agrees with tuple 2 on the values of A, attribute A. What does it mean? Let's check the other condition. If they agree on one attribute, then they also agree on the attribute B, if we want to assume this functional dependency. So if they agree with this, do they agree on the B one? You can see that 1 has a 4 and 1 has a 5. This is a disagreement right over here. We can say that A functionally determines B does not hold. And that's why you see it here, that A pointing towards B, or A functionally determines B does not hold. However, B pointing towards A, or now B functionally determines A hold. And how is it possible? When you look at B, a unique. B is a unique. They're all unique. Okay. And they all point towards one mapping. For example, 4 is pointing towards 1. 5 points towards 1. And 7 points toward. So it is a 1-to-1 mapping. Okay. We do not have one value in B pointing towards two values. Okay. So we have only 4 pointing towards 1. And this is what you need to assume. A functional dependency assumes a 2-1 mapping. Okay. Another reason why A functionally determines B doesn't hold, because our 1 points to two values. So 1 points to 4 and 1 points to 5. And that is going to default our assumption here of saying that a functional dependency always assumes a 2-1 mapping. Okay. So that's why we end up having A pointing towards B as not holding, because it has a too many mapping, and a B pointing towards A holds because it has a 1 mapping. So one instance of B only points to a single value. Let's look at keys. So if we have a set of attributes, or even just one single attribute as a unique identifier of tuples in R, and there are no subsets of those attributes that uniquely identify R, then we can say that those attributes, or that attribute X, is a candidate key. And we can look at the syntax here. We say if X functionally determines R, or if X is a unique identifier of R, R being our relation or our table, and no subsets. For this case, this is Y is a subset of X. If there are no subsets that can do the same job as X, okay, then we can say that that X is a candidate key for a relation R. Any attribute that is part of a candidate key is called a prime key. And we know it very well that one of the candidate key is chosen as a primary key of R. And of course, the primary key also acts as a reference in another table. full functional dependency. A functional dependency is considered full if removing any attribute from the determinant would break the dependency. So what does that mean? It means that all the attributes in the determinant are necessary in that functional dependency. An example, we already know that our functional dependency is written in this format. The left-hand side pointing towards the right-hand side. So let's look at the attribute. This time around, we have sets of attributes. We don't have one attribute as a determinant. So we have AB pointing towards C, okay? And we say that we literally say it out like AB functionally determines C. Or you can say C is dependent on attributes AB. So still concentrating on the left-hand side, we say that both A and B are needed because we're talking about the full dependency where all attributes of the determinants are necessary in that functional dependency. If we want that functional dependency to hold, we need both attributes. We need A and B. So you can say C is fully dependent on AB, or we can say AB fully determines C. Partial functional dependency. A functional dependency is considered partial if it is possible to remove some of the attributes from the determinant while still maintaining the functional dependency. That means not all attributes in the determinant is actually required, okay, to determine the values of the dependent. So still back to our same example where we have AB pointing towards C. We're saying that either A or B can be removed from their functional dependency from our left-hand side because they said it is possible to remove some of the attributes from the left-hand side, and the left-hand side is always the determinant. So let's try to remove A being removed here. We're going to literally remain with B pointing towards C. Okay. And we can say that C is partially dependent on determinant, which is AB, meaning that C is dependent on part of the key. It's not fully dependent on both of them. C is dependent on part of the key and part is partial. And that is why we say C is dependent on part of the key, but not full key. And the key here is AB. All right. Transitive dependency. A transitive dependency occurs when there is a functional dependency between attributes indirectly through other attributes. Let's look at this example. If A determines B and B determines C, that means A determines C, okay, indirectly. And we call that a transitive dependency. One thing we need to note that A is a prime key. A is the prime key. And we say prime key are part of the candidate key. So, meaning that it is a very important key that acts as a unique identifier. And B is a non-prime key. So a non-prime key pointing towards becoming a determinant is an indication that, hey, that is going to be a transitive dependency. And we put a note here and say an existence of a functional dependency via a non-prime attribute is a sign of a transitive dependency. And you can see our non-prime here is B. Okay, so A pointing to B, B is already depending on someone. And again, it goes ahead to point towards another attribute. And now that is an indication of a transitive dependency. And of course, we can conclude and say A determines C via B. transitively via B, or you can say indirectly via B, and that's why we call it transitive dependency. This is an example of finding functional dependencies in a given relation. And you're given the relation, which is basically R with attributes A, B, C, D, and E. And the data values basically which we are going to use to do our mapping using our formal definition of functional dependency. So the question is, which of the following functional dependency will not hold in the above relation? So let's test the first one. C determines E. Let's look out for any tuples that are matching, because we said for a functional dependency to hold, okay, the values must match in one attribute, and also if they're matching in one attribute, they should also match in another attribute. So let's see C. C, we have 5 and 3. We have 5 and 3 repeated. Okay, so these are two. The first tuple is a 5. This is a 3. The 5 and 3 basically repeated. So let's see our 5. All our 5 are pointing towards a 0. If you're looking at 5 and E, okay. And 3s, let's look at the 3. 3 pointing, and it fails. 3 fails on the second one, okay. 3 is pointing to 2, but it's failing to point to 2 again. So it fails the condition, okay. And since we are looking for those that are not holding, we can say it is part of the correct answer in this, if we consider this statement right over here, okay. So another thing we look at, the too many. One instance is pointing to 2. So a 3 points to 2 and 3 points to 3. That is going to fail that's going to fail our condition. Let's look at the other way around. We are testing C. We are testing E pointing to C this time round. And these are the values in E. E has 0, 2, and 3. 0, 2, and 3. Those are our values. Okay. Let's see where do they agree. 0 is agreeing to 5. That's correct. 0 is agreeing to 5. Okay. Let's look at 2. 2 agrees to 3. And 3 agrees to 3. Let's look at the mapping. The mapping right over here is 0 is 1 pointing to 5. Okay, sorry. The mapping here, we have 0 is pointing to 5. So all our zeros are pointing to 5. Our 2 is going to point to 3. 2 is going to point to 3. And our 3 is going to point to 3. 3 is going to point to 3. So look at the instance. The instance here have a 2-1 mapping. If you have a 2-1 mapping, the condition holds, as opposed to have a value having a 2-many mapping. So a 2-1 mapping holds. A 2-many mappings doesn't hold. Another example is A. Let's test A pointing to B before we talk about D. So A pointing to B, A is right here. There are only 2 unique values, so 1 and 3. Let's look at, and then B is all the same value, 4. Let's look at the mapping here. So we're going to say 1 is pointing to 4. So 1 points to 4, okay. Still 1 points to 4, okay, that's a good argument. 3 points to 4, 3 points to 4, and 3 points to 4 again. So this is a 2-1 mapping. Okay, one instance points to the dependent only 2-1. Okay. B pointing to C, or B determines C. Let's see this. B is all 4. So we have 4. 4, let's see how many values does 4 point to. So 4 is going to point to C, 5. The first time is 5. You can see that. The second time is going to go to the 3. Then again a 5. Okay. And then to 3. When you look at this, this 4 is being mapped twice. Okay. So this is a too many mapping, which basically doesn't pass the, it doesn't hold when it comes to a functional dependence. So this does not hold, this will hold. Let's look at D. When you look at D, our values are pretty much unique. And if you have an attribute that has unique values, then it's probably a candidate key. If it's the only one, then it's the primary key. In this case, it is the only one, so this is the primary key, and a primary key uniquely determines any of this. It could determine all the other attributes, so you can see that D can determine all the other attributes, the A, B, C, and E. Okay, and also it can determine a subset. It can determine only 2 AB. Okay, it can determine 3 of those subsets. Okay, because it can uniquely determine all the attributes. Okay, so let's look at E. Since we know that D is a candidate key, any attributes that will add, okay, that is composed to, okay, any attribute that appends to it, it will still give it the same power of a primary key. So this will also be a unique identifier, and it can also identify any attribute. It will do the job of D exactly. So find the enrichment activity 4.1 about finding a functional dependency in a relation under the assessment section. So pretty much what we just, the activity we've just done in class. This is what we talked about today, and our next class is basically finding attributes closure, and candidate keys.